Okay, let's have a class, and in the 30 minutes time, roughly we're going to talk about antimicrobials, because this is kind of the side topic of the lipids. But I want to talk about that because myself is doing a lot of the research about antimicrobials, and our group are doing that. So we want to talk about I would say antimicrobial chemicals. So related to the lipid section, so we want to talk about all those organic acids. So all of these, we will say it is a short chain fatty acids. And we will give you 5 examples. And it is, we say, GRAS by USDA FSIS. So what is GRAS means? Means general recognized as safe. That means they can using on the food product surfaces. Now FSIS is United States Department of Agriculture Food Safety Inspection Service. That's called USDA FSIS. And they are usually, most of the time, originally always say, it is natural existing. However, right now, more and more companies or industries, they do chemical manufacturing. But at the beginning, they do find in the natural, most likely it's in the plants. However, there is a big restriction. They have to use below or close to their pKa value. Okay, so this is something we want to give you opening remarks about antimicrobial chemicals. Now, what are they? Let's give you some of the examples to talk about that. So we gave you some of the examples. The first example, everybody knows, CH3COH, acetic acids. Okay, where the acetic acids comes from? It's from vinegar. And we talk about the pK value. So what is the pK value of this guy? The pK value is 4.2. I just want to make sure it's correct. And it works very well for bacteria and fungi. So I just say bacteria and fungi. Now, what is the concentration they can be used? 0.1 to 0.8% around. That's the first one. Okay, the second one, acetic acids, relate to that is we have a phenyl group, then we go COH. That's benzoic acids. Where is the benzoic acids comes from? It comes from a berry, which is a cranberry. People are saying if you are drinking the cranberry juice, well, good for the prevent urinary tract infection, for the urine health. Let's talk about that. The pK value is 4.8 around. It's good for fungi when they first comes out. Later on, they find the bacteria is working very well, and the concentration, it is actually very low. It should be less or around 0.1% to be used. That's benzoic acid, but we're gonna go back to talk about that. Next one, the structure is CH3, CHOH, and then COOH. What is that one? Is lactic acids. Lactic acids, we know it's coming from fermented food. And the pK value is about 4.7, 4.9. It's very good for bacteria. And the concentration could be 0.4 to 2.0%. Some places even using 2.5% for lactic acids. And the lactic acid is widely used on the beef carcasses for prevent the pathogen. Okay, next one. CH3, CH2, COOH. What's that? Probionic acids. That's probionic acids. Where this one comes from? Well, they isolated, they used from Swiss cheese, the fermentation process. The pK value 4.8, effective for bacteria and also for fungi. The concentration is relatively low, is around 0.3 to 0.5%. Okay, the last one, what I want to mention, this guy has a lots of double bonds. CH3, CH, 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 then goes COOH. That is sorbic acids. Sorbic acids, where that comes from, it comes from another berries or different type of the berries. pK value 4.7, work for bacteria well, and the concentration is relatively low, only 0.1 to 0.3%. So these are the major things they talk about for the microbiology textbook, for the chemistry textbook, talk about these. So obviously you can see these can belong into fatty acids, very short chain fatty acids. Now we want to talk about this pK value. What does that mean? So let's give you a review for the chemistry. I have all COOH. It's a weak acid. The weak acid that could be dissociated become all COO negative and the proton. But you know the reaction will not be completed. They could go either way. Then you have a pK value. We determined by pKa is pH at which the concentration of undissociated, which is all COOH, equals the dissociated. That's called pKa. And there is a restriction. We have to using a food products which are pH close to or below pK value. So let's say all these type of the weak acid, they are around 4.2 to 4.9. And most of the food products, what's a pH average? Let's say meat, around 5.0 to 5.5. So can they use? Yes, they can, but it won't be very effective. That is the reason when you read millions of papers talk about spray acetic acid, lactic acid on the poultry or beef carcasses, so you get 1 log reduction. 1 log CFU per gram reduction. That is the reason, because it is relatively above its pK value. However, we have to use it because that's required by HACCP plan. We have to do some of the intervention. Okay, so this is the first thing you need to know. So don't be surprised when you read all the paper. It is only about 1 to 2 log reduction, up to 2 log reduction. Now we want to explain to you a little bit about what's the mechanism for them to inhibit or kill bacteria. So this is go back to, we can draw here is, let's say, this is a bacterial cell. Okay, that's a bacterial cell. And they have internal, external, that's outside of the cell wall. Then I have a weak acid is coming. Okay, weak acid coming, you will see it's going to be RCOO negative with positive and go this way and go that way. There is a limitation that the only thing will happen is this undissociated one. The undissociated chemical can go inside, and the dissociated one will not go inside. That's the reason we need to prepare the solution. The pH close to pK value. In other words, this guy's concentration needs to be high, needs to be relative. So the reaction could go this way, become an undissociated format. Okay, when they come in, what they do? So let's say I have this guy come in. Then give you a very basic question. What is the internal pH of a bacterial cell? It should be around 6 to 7 or close to 7. It's a neutral pH. We know that you learned in the microbiology class. So what happened? This reaction go the other way. They will generate dissociated one and proton. This is not good because when you proton accumulated, their pH will be decreased and away from their optimal neutral pH value. So what they do, what's a bacteria do? Bacteria have to pump these things out. That's what we call it a pump outside cell wall. Okay, when they pump outside the cell wall, what they need to do? They cannot just naturally go out. They need the help of this guy. For the chemistry class, we need to make you a little bit complicated. We're going to draw it. H, OH, H, OH, H, CH2, go here, O. What is this guy? Everybody knows. That's ATP. And the bacteria need to hydrolyze ATP, become ADP, and the phosphate. They rely on their ATPase. If they use a lot of the ATP, what that will happen? Bursted by their metabolic process. So exhausted. Exhausted by metabolic process. This is the ideal model for why acetic acids, probionic acids, lactic acid can kill bacteria. However, in the real life, bacteria can survive in acid environments. Sometimes they could do change. They pumping out of proton, they exchange with potassium or sodium, those ions. They could exchange. And sometimes they have other mechanical reason they could survive in an acid environment, especially like we talk about E. coli, salmonella, they became acid resistant strains. What happened, if you own a steaks, you have an acid resistant E. coli 057H7, you further go ahead to do the cooking, they will generate cross protection, which means they are difficult to be killed during the thermal inactivation. Okay, so that is a basic mechanism behind it, the story. So we mentioned about this pKa value. This pKa value has to be low. And the preparing the antibiotic solution has to be low. Because all these pK value is very low. This gives you a challenge. Okay, we don't want those acid environments. You know the food contact surfaces, lots of the time, they will cause corrosive or some of the other issues. So what's the industry they do? Ian, can you move? What they do, they generate some other chemicals with the reaction. So we gave you an example using benzoic acids. Okay, so I had a benzoic acids like this. Okay, what I'm going to do, the idea is that I'm going to increase the pK value. So what I do, I'm going to react it with methyl. What is methyl? That's very simple. How they reacted? This is become a water out. So what they gonna become? You see the same thing? A phenyl group, COOOCH3. Of course comes out with water. What this called? Methyl benzo, let me just make sure, benzo 08. Methyl is coming from methyl, and OATE, this means carboxylic acids, which is right here. Okay, we can do more. People think using method is not good. So let's use a very traditional one. Everybody knows alcohol. So let's add alcohol. CH2, CH3. Okay, what's the reaction will be? This will generate a good stuff. COO, CH2, CH3. This is becomes ethanol benzoate. Okay, people think it's not very enough. We could do more. What we do, I'll give you another example. So that's still a benzoic acids. Let's add another CH2. What is this one? Propanol. When you had a propanol there, they're also going to be reacted, so it becomes COO, CH2, CH2, and CH3. Becomes a propyl benzoate. So what's a good thing? We can do long and long, long and long. The chain could become long and long. What's a good thing? pKa value could be increased from 4.2 to 4.9 the range, all the way go to close to 8.0. However, there is a bad thing happen. What's the bad thing happen? Oh, sorry, there's another good thing happen. With increasing the CH2 chain, carbohydrate chain of fatty acids, the antimicrobial activity is increased. However, there is a bad thing. What this means? The chain is long and long, becoming more like fatty acids, not like organic acids. What's the disadvantage of that? Longer chain, less dissolved in water. That is not good. We certainly want all the antimicrobials could be easily prepared in the water. We don't want to prepare in the alcohol solutions. This is especially tricky when we do the research. If you have an alcohol solution, you have antimicrobials, and your antimicrobials have to be dissolved in the alcohol solution. That means you need to set up a more control group. You need to make sure the antimicrobials is not coming from the alcohol, it's coming from the fatty acids, the long chain fatty acids. So this gives you a challenge. But it is a smart way. A very old traditional way to do is increasing the pK value is you react it with all types of alcohol. Ethanol group, we'll say, long chain ethanol, then could increase it, but the chain has to be appropriate. Because whenever you add a chain there, they are less dissolved, soluble in the water. Okay, so this is something we want to mention and emphasize to you. Now let's go back to have one topic what we talk about in the lab. So I did many years with our extension group, Small Farm Conference Center. We are talking about is the Sanidate 5.0. So we did tons of research, published lots of paper about that. So what is that one? It is very interesting. Actually, we could talk about that. This is a reaction between acetic acids and hydrogen peroxide. So this is acetic acid. And they will be reacted, generate the products is CH3, CO, O, and OH. What is this one called? Peroxy acetic acid. This peroxy acetic acid, acronym called PAA, for itself is approved to be used on the food contact surfaces. It is actually approved by the Organic Association, so you could use it even in the organic process. Now the company, which is very smart, what they do, they combine with these products because they are adding more H2O2, want the reaction more completely on that way. So what they do is they combine H2O2 with PAA. Of course, they need water, and this combined is 23%, the other is 77%. Once you combine them together, become a new product called Sanidate 5.0. Now, what is the approved concentration they could use is 0.05 to 0.18% in fresh produce processing water. And we did a lot of research. Sometimes we show this concentration is good, sometimes we show it's not a fact. We have to increase to 0.25. And our paper even got rejected because we increased into 0.7%, and we find it can completely prevent the cross-contamination of salmonella. So the dose issue is always important. Now we want to talk about this guy, since it's a food chemistry class. Why this guy could inhibit a bacteria? And I want to tell you, if you do lots of the research, you do the literature review, PAA actually could kill more than 2 to 3, sometimes to 4 log. It is higher than acetic acid. These are basically 1 to 2 log. Why? Do you remember this guy? This guy could release, become what? Hydroxy radical. And I said that this is a very energized. It's a very energized electrochemical. In our lipids oxidation class, we mentioned the electron arrangement actually matching the electron arrangement of the sorbitol of the double bonds. And here, we not talk about the lipids oxidation, we are talking about oxidizing bacteria. Where are they? Cell wall structure. So this is go back to our basic, we go back to our basic general microbiology class. So let's say I had a gram-negative bacteria, let's say salmonella. What gonna be the structure looks like? We know this is fluid mosaic model. Okay, we're gonna go a little bit detail. This is not biology 101. Okay, we know this. And then for gram-negative bacteria, what's a very typical symptoms or characteristics? This is a very thin peptidoglycan. And then up the top, what you find there? You'll find another layer of fluid mosaic model there. You have another one there. But more important here, you have LPS, which is a lipopolysaccharides. It is more important LPS will generate endotoxin. That is why salmonella is a problem. So where are the places this hydroxy radical could attacking? Obviously, sometimes here, could also for the LPS. So let's talk about what's the structure of this lipopolysaccharides there? Oh, sorry, what's the structure of this phospholipids there? If we want to dig this one out, we could draw a very good picture, which is NH3, go CH2, CH2, then go here is OP phosphate, then go down CH2, CH2, then we go here, CH2, CH, go here, CH2, then you go here, CO, go here, what you find? Very long chain. Then you go here, CH2, CH2, CH3. What are these structures? This topic right here, an ethanolamine. This topic on the top is ethanolamine. This is a phosphate, you know about that. How about here? It's a glycerol. How about here? That's a fatty acids. And for a bacteria, a generic model, this is C16.0. How many gases? If you see all the microbiology textbook, yes, it's double bonds. It's no double bonds, so it's hard to do. But with a very energized hydroxy radical, obviously this guy couldn't let it be oxidized, which means it could cracking down the cell wall structure, which is target the cell membrane system, because you have a phospholipids. Now, what's the energy for that one to using? Around 110 kcal per mole. We talk about that. Is that right? When you have a pentadiene, it's go down to 85. This is pretty high, but it still can do. So that's the places it could happen, which is oxidation. Now, another place is LPS. So what's that looks like? What's the LPS? Lipopolysaccharide. So what it looks like? At the beginning, you will see there are lots of the chemicals looks like this. They go here, looks like that. Then you go here, some looks like this. Then you go here, it looks like that. This area, O antigen. It's a ceramic. That's what the 0157H7 comes from, because it's your serological typing 170. Not for bacteria, for E. coli. Okay, now you go here. In the middle, if you draw a picture, looks like that. Looks like this. Okay, just a brief picture. This is called the core area. Could be different type of the modified sugar. Now you go down. You're gonna have this guy comes out. They draw like this. Lipids A. So, where they could go? This OH could attack you. Once they're attacking the lipids A, the endotoxin generation could also be decreased. So that's some of the thing people have not been looking for, but if you look at the chemistry books, they will say, oh, peroxyacetic acids, they will be attacking the cell membrane system, the lipid system, and even the protein of a bacterial cell. But where are the possible locations? And these are the possible locations. But haven't done much research about the detail about that. Okay, by the way, it's not a full microbiology class, but I will just let you know. Dr. J will ask you a question all the time. What does this mean? What does E. coli 157H7? I already say O is O antigen ceramic. You should say modified carbohydrates. What is H? That's flagella. Okay, that will be the question from his exam. I know a long time ago. I asked this question in my other classes also. That's what O157H7 means. O is that antigen. That is from the LPS. H is a flagella. Okay? So, yeah, I think it's already past 1:45. That's what I have for this short section about the antimicrobials. We talk about organic chemicals, and we talk a little bit about what we research did about Sanity 5.0 related to the structure of the cell wall for gram-negative cells, the possible metabolic reasons. Okay?